Okay, well, thank you very much. I'm here today to talk about microfiltration as a way of rapidly detecting pathogens. I'm speaking on behalf of our team, some of whom are featured in the picture, and also our team, which includes OTC, which has helped us both in positioning this from a business perspective, marketing it, and also from maintaining and getting IP. So basically what we're trying to do is look at preventing many cases of food poisoning. And there's a lot of cases of foodborne illness. It's estimated about 1/6 of the U.S. population is subjected to this. And overall, basically the way to prevent this is rapid detection. So we've been working on this for about 7 or 8 years. And what we found is that prevention requires rapid detection, and rapid detection requires rapid sample prep. And that's been the key. Right now, the way these pathogens are detected is culture is carried out to amplify the number of microorganisms there, then probe for the presence of the pathogens. What we've done is we substituted microfiltration and solved many issues involved with microfiltration, including fouling, so that, in fact, we are trying to get a shift in a core assumption that one needs to use culture and petri dishes in order to detect pathogens. What we're saying is can be replaced with physical methods by adding enzyme to a feed stream, packaging the technology properly, and then avoiding membrane fouling so that you can rapidly concentrate microorganisms. Well, the way this works, and this is this blue diagram, is you add enzyme and your extract in a reservoir. You pump it around through a peristaltic pump. It goes through a hollow fiber. The hollow fiber itself filters out the water. In order to avoid some of the fouling issues, we also have a stream on the permeate side. This is then recycled, and after a few minutes to a few hours, the volume will decrease from anywhere from 500 mils or a liter down to about a half a mil, at which point you have a very concentrated sample of microorganisms, which can be probed for pathogens. One of the keys here is you must recover the pathogens in a viable form. If they're dead, it's not relevant in this case. So what we did, working together as a team, biomedical engineering, agriculture engineering, also in food science, in the biology department with other collaborators outside of Purdue, we put together an instrument that in fact encompasses all of these concepts. The way it works is you put a sample in, and after 4 minutes already you can see the samples decrease from 50 mils down to about 5 mils. After 6 minutes, this is for a 50 mil sample, we have a sample tube, and this is controlled by a laptop in this case. We then did PCR. The PCR shows that we're able to detect 1 CFU per gram of salmonella in spinach. And this turns out to be a big issue for FDA. We entered this in the FDA food safety contest with 49 other companies and won it as a university. Okay? And so we're continuing to work with them. We had to use initial volume of 500 mils instead of 50 to detect it. Now what we've done is we've actually now increased the number of samples we can handle. And we're working closely with FDA, and that's one of the requirements they would have in order to test this technology in their lab and validate it. And so we now have an instrument that does, thanks to Kurt Foster and his team, an instrument that is able to process 8 samples simultaneously. So what's needed now really is for us to complete the FDA validation and testing. That will give us the specifications we need. We're looking for a manufacturer of the instrument once it's proven so it can be more robust